Welcome to Lesson 9E, Series and Parallel Cleaners. We're going to talk about cleaners in series and in parallel. Before we start, I want you to note that this analysis that we're doing today is for gaseous air pollutant, where we've dropped the subscript J, or a monodisperse aerosol, so we're dealing with one diameter at a time. But we can extend this to a polydisperse aerosol. We just need to take a little bit more care because these cleaners have great efficiencies. The cleaning efficiency for any cleaner will be different depending on the particle diameter. For gases, it's really not an issue. That being said, let's do parallel first. I'll do 2 cleaners for simplicity, and then we'll extend that to M cleaners, any number. So let's consider this diagram. Suppose that C in is coming from the left. It splits off into 2 parallel flows, but the concentration hasn't changed. So those are both concentration C in. The flow rates can be different though, so we'll call this Q1 and Q2. We have the same Q1 and Q2 coming out of the cleaners, assuming there's no leaks. We also assume that the volume fraction of the air pollution is so small that Q is not changed significantly. Let's call C1 the mass concentration coming out of cleaner 1, and we know that C1, by definition of a cleaner, this is a removal efficiency eta, so we would have C1 is 1 minus eta 1 times what's coming in, which is C in. Similarly, C2 is 1 minus eta 2 C in. And eta 1 is not necessarily equal to eta 2, nor is Q1 necessarily equal to Q2. What else do we know? We know that the total Q has to equal Q1 plus Q2. That's just conservation of mass. Again, assuming no leakage. This is the bulk air flow rate. Let's define Fj as the fractional flow rate, where J is the cleaner number. In this case, there's only 2, 1 and 2. Fj is Qj over Q. So it's the flow rate coming through cleaner J divided by the total flow rate, the fractional flow rate. So here Q1 is F1 times Q because F1 is Q1 over Q, and similarly for F2. So these are all for the bulk air flow rates. We haven't said anything about the concentrations yet. Now let's consider the species mass balance. Recall that m dot of some species J is CJQ. Now let's drop the J subscript for species like we did up here. We didn't have any J's up here in our diagram, but instead let J be the cleaner number, which we're actually already doing with these equations, calling cleaner 1 and cleaner 2, and with these mass concentrations C1 and C2. Let's do a little algebra with these species mass flow rates. We had this equation above, C1 equals Cn times 1 minus eta 1. Multiply by Q1 everywhere, and then let Q1 equal F1Q, as we also defined above. So we have C1Q1 is Cn F1Q 1 minus eta 1. Similarly, for the second unit, we get the same equation except the subscripts 2. Overall then, when we look back at the diagram, the mass flow rate coming out overall is C out. The mass flow rate of this species coming out is C out times Q. But that has to be a combination of C1 times Q1 plus C2 times Q2. Overall then, the mass flow rate of this species at the outlet is C out Q, and that's equal to C1 Q1 plus C2 Q2. And we can use the right-hand sides of this equation that's boxed up here to get this in terms of F1, F2, and Q, and C in. So this is C1 F1Q times 1 minus eta 1 plus C in F2Q 1 minus eta 2. This is an intermediate term here, so if we look at the remaining terms, you see that there's a Q in each one. So we can write an expression for C out is C in times the quantity F1, 1 minus eta 1, plus F2, 1 minus eta 2. Remembering that these F's are fractional flow rates, don't confuse those with mass fractions as we talked about at the beginning of the course. So that's our final expression for C out. In terms of an overall removal efficiency, we'll call that eta overall. Well, like any cleaner, we define this as 1 minus C out over C in. And for our case, we're talking about these 2 cleaners in parallel. And what we're essentially saying is that if we put kind of a box around this whole thing and assume that this is just one big cleaner, this is equivalent to a cleaner with flow rates Q and mass concentrations C in and C out. You can even physically put both of these cleaners as in this schematic diagram and put them in a box so that you don't even know that there's 2 cleaners in there. You just see this. That's what we're trying to get, the overall efficiency. So again, it's just 1 minus C out over C in. Well, we can get that from here. 1 minus the quantity F1, 1 minus eta 1, plus F2, 1 minus eta 2. And I apologize if my etas look a little bit like n's. If I want to do it right, I should do that. my n's are typically like that. Finally, we can extend to m cleaners, where m is any number of cleaners. And you can see this is just a summation, so we can write sigma j equal 1 to m of fj 1 minus eta j. So this is the overall efficiency for m cleaners in parallel. For example, the simplest case would be if you have m identical cleaners, so the removal efficiency is the same for each of them, and you split the flow evenly amongst them all. So for example, if we have 4 identical cleaners in parallel, we have a Q coming in, the same Q coming out. We split them, each one of these would be Q over 4 for all of these. We have some C in and some C out. So this equation would reduce to then eta overall is 1 minus, and then we're summing the same thing m times, so this just gives us, in general, Q for any of these cleaners, if they're all divided evenly, is Q over m, which means that Fj, which is Qj over Q, will be 1 over m. So this equation up here becomes, for this simple case, 1 minus. We're summing over m of them, and they're all the same, so that just gives us an m in the numerator. The Fj gives us an m in the denominator, and then we have 1 minus eta j. By the way, each of these has the same eta j. So the m's cancel, and then the 1's cancel, and we have eta overall is equal to eta j. Same as one big cleaner of that same removal efficiency. And that makes sense, because if you have 4 or 8 or whatever identical cleaners, you're going to have the same overall efficiency. There's no way to get something other than that same efficiency. Now let's consider cleaners in series. For this one, there's no F involved because the Q is the same through each cleaner, again, assuming there's no leakage. So there's no fractional flow rate required. Now let's analyze this one. C1 is coming out of cleaner 1, so C1 is equal to 1 minus eta 1, C in. C2 is 1 minus eta 2 times what's coming in, which is C1. And then I can use this equation above to write this as 1 minus eta 2, 1 minus eta 1, C in. And you can see what's happening here. The next one would be 1 minus eta 3 times C2. That's what's coming in. And then you use this to get 1 minus eta 3 times 1 minus eta 2 times 1 minus eta 1 C in. So for m cleaners in series, then, we can extend this. You can see the pattern to C out. When you finally get to the end here, Cm is C out. So C out, or Cm if you want to call it that. I'll just reorder these 1 minus etas from up here. 1 minus eta 1, 1 minus eta 2, 1 minus eta 3, and we keep multiplying those till we get 1 minus eta m for the last one, quantity times C in. And then similarly, we can write an overall efficiency, which is always 1 minus C out over C in. This just ends up being 1 minus everything in the square brackets. Now these 1 minus etas are all multiplied by each other, so we can't use a sigma, but you may or may not have seen this symbol before. Eta overall is 1 minus capital pi j equal 1 to m of 1 minus eta j for m cleaners in series, where this pi, capital pi, don't confuse that with 3.1415926, etc. pi. My brother is one of those guys who memorized pi to like 1,000 digits one time when he was in high school. There's a YouTube video where they sing the digits of pi to help you memorize it. I'll share my screen.
100 digits of pi. 3.14159, this is pi, followed by 2653589, circumference over diameter 79.
Thank you, BJ. I'm sure all the other students appreciate that. You're welcome. So this pi is like a sigma, except for products. We multiply instead of adding. Again, let's look at the simplest case. If you put m identical cleaners in series, think about what this equation is going to do. You're going to have 1 minus, and then you're multiplying 1 minus eta j times 1 minus eta j m times. So eta overall will be 1 minus, and then 1 minus eta j times 1 minus eta j times 1 minus eta j m times, which gives you an exponent m. This is a simple case for m identical cleaners in series. And then here's a summary for these equations for m air cleaners in series and parallel. So the parallel one and the series one, I just summarized those equations and give you the definition of this volume fraction. These are also on the equation sheet. Now let's do an example. We have air coming into cleaner 1. There are 4 cleaners in parallel, which we call cleaner 2. These are all identical, but they're different from cleaner 1. And then they combine back together for our outlet. So there would be some overall Q coming in and out, and there would be a C in, and there would be a C out. And I give you the cleaner efficiencies. So 1 is not identical to 2. We give you the bulk flow rate Q. And this air is at SATP, so I give you the properties. I want you to calculate the overall removal efficiency of these combined cleaners. And I put the equations here for convenience. So first, let's look at the 4 parallel cleaners. Treat this as kind of one big cleaner as we talked about previously. So this is like one cleaner with removal efficiency eta 2. So effectively, we have this. We have cleaner eta 1, and then we have this big cleaner eta 2 that replaces those 4 in parallel. So we have the same flow going through all of them. We have a C in, a C1, and a C2 equals C out. So these are now 2 cleaners in series. So we want to use this equation so that eta overall is 1 minus eta 1 times 1 minus eta 2. And I plug in the numbers. Now be careful here. We gave these in percent, but the actual numbers I would plug in is 0.91 and 0.95 for these cleaner efficiencies, not the percentage values. Otherwise, you're going to end up with some really funny numbers here. So I get 0.9955, but I asked for the answer in percentage. So eta overall is 99.6%, which, by the way, is much greater than either one of these by themselves. So we get a total of 99.6% removal efficiency. The bigger the number, the better, of course. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.